Thank you so much, Bayun and Augustin, for joining us in the lab today to answer some questions about setting up a power system in your lab. So the first question I have for you today is, let's say you have a motor, propeller, and ESC you want to test. How do you calculate how much power you'll need from your power system?
Typically, it's the ESCs that dictate the system power requirement. For example, here we have an APD UHV 28S 300 amps. That means up to 28 cells LiPo, equivalent to 300 amps continuous, around 104 volts. Multiplying those numbers together, we can determine the total power is around 35 kilowatts.
However, sometimes it's quite challenging as you may want to pair the same motor with different ESCs. So it can be time consuming to check it one by one. The golden rule is estimate the power through thrust. Let's say if we are planning to test a powertrain capable of 120 kg force at full speed, the overall efficiency will be most likely around 3 gram force per watt. This means for 120,000 gram force, we shall expect at least 40 kilowatt of continuous power. We may get a power system for 45 kilowatt to be safe.
Okay, so next question. How can you make sure you size your ESC properly for your motor?
For example, if you have like us a 30 kilowatt motor, 120 volts operating voltage, you need an ESC that have the same operating voltage and more operating current. In our case, we have a 120 volts, 320 amps max for the ESC. It's very well for our motor.
Well, as long as we determine the necessary continuous current power of the motor, then we can simply choose the rated voltage and the necessary current for the ESC. It is always good to keep a buffer on its maximum rated current.
What other variables are important to keep in mind?
I'll name 3. So the first one is the difference between continuous current required by the powertrain and the maximum current supplied by the power source. Motors and ESC will have dynamic fluctuations and spikes, even at a looks like constant speed, and we must reserve a buffer for those current spikes. And the second one is the supply voltage and the kV of the motor. We always want the motor to drive the propeller at the right speed, not too fast, not too slow. Too fast can damage the ESC, too slow can mean we are not getting the thrust we want. This is more important when using batteries because we cannot easily add or remove a cell. The third one is the C rate of the batteries. Most batteries have a maximum charge-discharge rate that is also determined by its capacity. If the battery cannot discharge fast enough, we will not get the current that we want.
It's important to keep in mind the max load of each component. For example, the max torque of the motor based on the number of poles. If the torque is too high compared to the RPM, the motor can be overloaded and create huge current peaks, and the peaks can create instability and damage the power source, create overheating on the power supply, etc.
Let's say you have a coaxial or distributed electric propulsion system. How does that affect your total power requirements?
Well, if you have a coaxial system, you will need the same voltage but double the current of a single motor system. It wouldn't be any different except that we need to calculate the overall power needed for all the powertrains combined, as most of the time they would use the same power source. 2 extra points to pay attention to. The first one is the capacity of the battery as the total discharge current becomes double or multiple times higher, which will require a higher C rating or higher capacity. The second one is the use of the capacitor banks on the DC side of the ESC, as one motor can regen in deceleration and its excessive current can damage the other powertrains.
For coaxial installation, the 2 propellers have aerodynamic interactions, which affect the total power requirements. This is true whether you have 2 identical props or 2 propellers with different size. Assuming you have 2 equal propellers, rather than requiring 2 times the power, it's more 1.7 compared to a single propeller setup. Depending on the rotation speeds, etc., the propeller in the back will have a smaller torque and smaller thrust at the same RPM that can reduce the total torque and the total power.
And when would you use a battery pack versus a power supply?
We use both at Tyto. For bigger powertrains, we tend to use the battery pack as it is more resilient and the possibility of regenerating energy back to the battery makes it slightly more reliable compared to AC/DC power supplies. However, for smaller powertrain testing, we tend to use power supplies. They are very flexible, adjustable, and they can output voltage varying from a few volts up to 100 volts, which can fit almost all the ESCs we have in-house.
Both can be used as a power source. The main problem with using a power supply is that it needs to be plugged into a wall, and it does not react well to huge current peaks or voltage drops. Power supply converts AC to DC using diodes after it stabilizes it with capacitors. Current peaks can damage and overheat capacitors and diodes. Concerning batteries, the main problem is the charge and discharge time. It takes a long time, several hours, to charge the whole system. Batteries offer an advantage due to their chemical storage, which means the current drops can be better absorbed. Furthermore, batteries are more flexible. Stack them, move them anywhere, and assemble them in series or parallel, depending on the voltage or current you need.
What are some safety considerations when working with batteries or a power supply?
Well, I'll cover two main considerations. The first one is the reverse current, or regen of the power when the powertrain stops. If the ESC doesn't have any capacitors on the DC side, most of the power supplies do not handle that reverse current well. In this case, you need to inquire with the manufacturer of the power supply and add a buffer such as a diode or capacitor. The second one is monitoring of the temperature. It can be very dangerous if the battery overheats. Generally, the BMS on large-scale battery bank should have a temperature sensor that will automatically initiate the cutoff when the internal sensor detects a temperature that is too high. But if you are using LiPos or small-scale power systems that do not have a management system, you may attach extra temperature sensors or thermocouples and set a safety cutoff for that input in the flight stand software. We provide these probes with each flight stand, and you can buy extras on our website.
It is essential to have a safety switch to help you deal with any issue that can appear. The safety switch should shut down the power source, which cuts the energy to the power train. It's important that the safety switch is near to the operator and far from the propulsion system. In our case, the operator and safety switch are in a separate room from where the test is taking place. Same goes for the breaker and a power supply. It is also important to understand the danger of electrical power. When dealing with high voltage system, you should wear high voltage safety gloves when you manipulate electrical components. It is important to have an extinguisher for each type of power source. Batteries require a different type of extinguisher than a power supply. Due to the current and possibility of overheat, you should be prepared in case of the batteries, power supply, or motor catches on fire.
Do you have any other tips for setting up or operating a power system?
Well, read your product user manuals carefully for instructions, specifications, and safety limits. This can save you a lot of time and effort in the long run and help you keep yourself and your equipment safe.